Hello everyone, Aaron here. Welcome back to Leetcode. Today we're looking at converting a binary search tree to a greater tree. I will be honest, I have absolutely no idea what a greater tree is. So let's have a quick look here. Given the root of a binary search tree, convert it to a greater tree such that every key of the original binary search tree is changed to the original key plus the sum of all keys greater than the original key in the binary search tree. And then we have the definition of a binary search tree. We have the root, everything on the left is less than that, everything on the right is greater than that. Okay, so this node is going to be the sum of everything else. This node is going to be the sum of nothing else. This is going to be the sum of everything there. So this feels... We're doing a lot of tree problems lately, and this is very much going to follow the same set of rules. We have a recursive data structure, so we're going to end up with a recursive algorithm. It seems that we're basically going to do a rightward walk. We're going to take everything on the right-hand side of a node, add it up, set that to the current value, and then recurse down on the left-hand side, working our way through. So I think what we do is we basically are going to go our usual condition for tree algorithms. If the root is equal to null, return null. And then what we want to do is we want to go down, convert the BST, root dot right. The good thing about this is this will have been replaced with a 15. So when we add the 6 to it, 6 plus 15 is 21. So we are done. I think I'm going to need a helper here, aren't I? Just so I can propagate the value through. Let's do that. It's easier if it's a parameter in the function. That way I can pass it around explicitly, and I don't need to try and think, where am I reading this value from? Because, for example, this one here, I need to read up into the parent. That's a bit gross. So let's not bother with that. Oops, that's the wrong key. I'm used to Vim and Emacs style keyboard shortcuts, so this is not... The default for Leetcode doesn't quite fit my brain. Alright, so back into where we were. So here, if I'm starting in this node, the total so far is 0, so I don't care. I'm going to keep digging, keep digging, keep digging. So then I get to here, and then I'm going to do root.val is equal to actually, hang on. What do I want here? Do I want it to return both the tree node? If we're going down here, I'm not 100% sure here. So if I've built up to here, this one I know is now of the right size. So the new value is going to be tree.val, just automatically. And then I want to do a so hang on, that's the right. That's that one. So the right is going to be convert BST helper root.right on the total, whatever we've got so far, so 0, 0, 0, 0. The new val is the tree value plus the root value that we're currently looking at. And then we're going to go down the left. We're going to do a convert BST helper on root left, but we're going to do it with the new, let's call that new total. And we want to return a new tree node that consists of the new total, the left and the right. Okay, let's have a quick think about this because I've managed to get myself slightly tied up in knots here. Right, so if we're looking at the 8, the root has a value of 8 and its left and right are nulls, but we've passed down a total of 0. So we're going to go into the right, which is null. So it's going to bail out with a 0. The new total is going to be 8 plus 0. That should be right. This needs to be a bit of a change, doesn't it? If the right is null, we want to get a 0. Else we want whatever the value is. Yeah, because if the tree was null, then we're in trouble. So this one here, yeah, we returned null. So to get the right.val, well, it's going to be 0, and we're going to add on the root value. Then we're going to go down the left, which is going to give us a null, and we're going to return a new tree node, which is going to look exactly the same. That's going to pass up to here. This was given the total of 0, but now we've gone down the right-hand side. The right is not null, so we're reading right.value, which is 8. We're going to add on 7, which gets us to the 15. The left is null, so that's absolutely fine. We come up. We've got a 15 on this side. Plus 6 is 21. We're going to go down on the left with the 21. Here, the right is null, so we're going to get 0 plus... Oops, that shouldn't be 0, that should be number, shouldn't it? If that's a null, we want the number. And come up. Yeah, because we hadn't... Number. Total. Because, yeah, so that should be total. Come up. Ooh, I think we may have a problem here in this particular algorithm. But I don't quite know what it is yet. This one's surprisingly hard. So there's nothing on the left either, so that's total plus, so that's 21 plus 20, plus 5 is 26. That comes up here. Hang on. That's a problem, because this now needs to know 26, not 21. So we just can't do this. What we need is effectively to pass up both the right and the new total. In fact, we'll call that the right total. This is the right total plus the root value, and now I want to do the left plus the left total, which is the new total, and we want to return a new tree, which was the new total. But alongside that, we want to make sure we're returning the left total. So this annotation is no longer correct. Oh, I don't actually know how to annotate a pair in TypeScript. So dirty little secret is the first time I used TypeScript was the first video I made for this channel. So I'm kind of still learning some of these things. Oh, perfect. you can apparently just write them inside an array like that. Perfect. Most languages would use parentheses for this, but that's not what we're doing here. So finally, we want to do let new tree. Something I don't care about is the convert BST helper of the root starting at 0. Return new tree. Right, let's have another quick look at this. We go down here with the, well, we know this bit is fine. We've got a left total here running of 15. No, let's run it all the way from the beginning. So it runs 0 here, 0. We go down to the right, we get the null, and the total is still 0. So total 0, new total is the right total, which is 0 plus the root value, so we get 8. And we go down here, we're passing down the 8, and that's going to come up. So the left total is 8, and the new total is 8. We return a new tree node filled with the 8 and nothing. Pass that up with an 8, add to that to the 7. So we're going to get 15 for the new total. And the left total, well, that's a null, so we're going to keep the 15. We're going to go up here. We're going to go to 20. We're going to add the 15 to the 6 to get 21 for the new total. We're going to go down here, and we're going to add. Well, that's going to all be 21. We're going to add 5 to it, so we're going to get 26. So we're going to return a tree node with the 26 in it. We're going to come up here and we're going to pass up the left total. So this is going to see 26, and we're going to add 4 to it. So we're going to get 30, and then we're going to come down here, passing down the 30. Well, we're going to head this way, this way, this way. 30 plus 3 is 33, plus 2 is 35, plus 1 is 36, plus 0 is 36. I actually did that store the value correctly. Yeah, it must have. Because the total came down here at 30. And we added 3 to it, and that's what we're storing here. Okay, I think this works. Let's give it a go. I've probably mucked up some syntax somewhere, just because I'm not used to using TypeScript in this way. Oh, no, it got accepted there. Let's see what happens if we actually submit it. Fingers crossed, can't see any immediate problems. Alright, runtime 132 milliseconds, faster than 60%, and we use less memory than just 30%. So it wasn't a terribly efficient solution. It was relatively fast. So one thing I dislike about these is we don't see the distribution. This could be if I manage to knock off 1 millisecond, suddenly I'm faster than 90% of the solutions. They're all about the same. It's difficult to know what's going on here. Possibly because it's a recursive solution, it's all going to get a bit messy. Function calls are expensive. But because we're doing a double recursion here, it's kind of hard to know how to make this more efficient easily, because we kind of need 2 stacks. Basically, I think this is the tidiest solution. I'm happy with what we've got, and I think we'll leave it there. Thank you very much for watching, and I will see you all next week. Bye! Doesn't quite fit my brain.